The universe is dominated by a ghost, an invisible force tearing space itself apart. This is dark energy, the cosmos' greatest secret. By the end of this journey, you will understand the hidden forces that control everything from the largest galaxies to the smallest particles. We will venture into the void to discover why empty space is not empty at all, and how quantum fields hum with the energy of creation. How much of reality do you think is truly invisible to our eyes? This runaway expansion of the cosmos presents a profound conundrum. Think of two distant galaxies, not merely drifting apart but actively fleeing from one another at an ever-increasing speed. It is as if the fabric of space itself is stretching, pushing everything apart faster and faster. This observed acceleration is the primary clue pointing to the existence of dark energy. For most of the 20th century, scientists believed the universe's expansion, born from the Big Bang, was gradually slowing down due to the relentless pull of gravity. The collective mass of all the galaxies was thought to be acting like a cosmic brake. Then, in the late 1990s, two independent teams of astronomers made a shocking discovery. By observing the light from incredibly distant stellar explosions called supernova, they found the expansion was not slowing at all. It was speeding up. This revelation turned our understanding of the cosmos on its head. It suggested that a mysterious, repulsive force overwhelms the attractive force of gravity on the largest imaginable scales. This force, dark energy, now appears to dominate the universe's dynamics, dictating its ultimate fate. The nature of this force is arguably the greatest puzzle in modern physics, a fundamental gap in our knowledge that points to a hidden engine driving the cosmos. To grasp what this engine might be, we must first look at the leading candidate for this mysterious influence, a concept that redefines the very meaning of nothing. That rejected idea, his so-called greatest blunder, was the cosmological constant. Albert Einstein originally inserted this mathematical term into his theory of gravity to force the universe into a static, unchanging state, a notion he later abandoned when the expansion of the universe was discovered. Decades later, this very same concept was resurrected to explain the accelerating cosmos. The cosmological constant proposes that empty space itself is imbued with a fixed, intrinsic energy density. Think of the vacuum of space not as a true void, but as a stage with a fundamental, unchangeable property. This energy, woven into the fabric of space-time, exerts a gentle but relentless negative pressure, causing the universe to expand at an ever-increasing rate. It is a beautifully simple idea, and it fits the observational data remarkably well. Yet this elegant solution creates one of the most profound embarrassments in all of theoretical physics. When we try to calculate this vacuum energy using our best theory of the small, quantum mechanics, the numbers do not just disagree, they scream in contradiction. Quantum theory suggests that the vacuum should be a seething, turbulent sea of virtual particles popping in and out of existence, generating an energy density so colossal it should have torn the universe apart in a fraction of a second after the Big Bang. The predicted value is a number with 120 zeros after it, far greater than the gentle push we actually observe. This is not a small error. It is the largest discrepancy between theory and experiment in the entire history of science. How can our understanding of the largest scales of the cosmos and the smallest scales of the quantum world be so catastrophically incompatible? This staggering problem forces physicists to consider that dark energy might be something far more dynamic and strange than a simple constant. This staggering discrepancy between prediction and observation demands a more radical idea. What if dark energy is not a constant feature of space, but something that changes? This leads us to the second candidate, a concept called quintessence. Imagine a field that permeates all of space, just like the cosmological constant, but one whose strength can ebb and flow over cosmic time. This is not a static stage, but a dynamic, living entity. Quintessence is theorized as a fifth fundamental force of nature, a new kind of quantum field that could slowly evolve, its energy density shifting as the universe ages. This dynamic quality offers a potential explanation for a key puzzle. Why did the universe's acceleration only become dominant relatively recently in its 13.8 billion-year history? A constant force would have always been there, but a dynamic field could have lain dormant for eons, only awakening to push the cosmos apart in its later chapters. The nature of this hypothetical field is not just an academic curiosity. It holds the key to the universe's ultimate fate. Different models of quintessence paint wildly different finales for our cosmos. In one scenario, the field gradually weakens, leading to a gentle, eternal expansion where galaxies grow ever more distant and cold. But in a more dramatic possibility, the field could grow stronger and stronger over time. This could lead to a cosmic catastrophe known as the Big Rip. In this future, the repulsive force of dark energy would eventually overcome all other forces. It would first tear apart galaxy clusters, then individual galaxies. As the acceleration intensifies, it would rip stars from their solar systems and planets from their stars. In the final moments, it would overcome the very forces holding atoms together, shredding the fabric of space-time itself into a meaningless mist of particles. The search for quintessence is now a driving force in cosmology. Is the strength of dark energy the same today as it was 5 billion years ago? To find out, astronomers are building powerful new telescopes to peer deeper into the past, measuring the cosmic expansion rate with unprecedented precision. They are also scrutinizing the faint afterglow of the Big Bang, the cosmic microwave background, looking for subtle imprints that might reveal the ghostly touch of a dynamic field. The answer will determine whether our universe is destined for a quiet fade or a violent end. And this search for the engine of cosmic expansion forces us to confront an even more fundamental question. What is the true nature of the void that makes up most of our reality? To uncover the universe's ancient secrets, we must listen to its oldest whisper. This whisper is the cosmic microwave background, a faint afterglow that has been traveling through space for almost 14 billion years. It is the cooled and stretched remnant of the very first light that could travel freely through the cosmos, released when the universe was a mere 380,000 years old. Before this moment, the universe was a hot, opaque plasma, too dense for light to escape. As it expanded and cooled, atoms formed, and the universe suddenly became transparent. That first flash of light, once blindingly bright, has been redshifted by the expansion of space into a uniform microwave glow that permeates all of existence. This cosmic fossil is not perfectly smooth. It contains tiny, telltale variations in temperature, minuscule ripples that are 1 part in 100,000. These anisotropies are a frozen snapshot of the infant universe's density fluctuations, the seeds from which all cosmic structure would eventually grow. Satellites like the Planck mission have created exquisitely detailed maps of this background radiation, charting these hot and cold spots across the entire sky. The patterns in this map are a cosmic code, and when we decipher it, it tells us the universe's fundamental composition and shape. The data overwhelmingly indicates that the cosmos is geometrically flat, and it gives us our most precise recipe for reality. According to this ancient light, the ordinary matter that makes up stars, planets, and us constitutes only about 5% of the universe. Dark matter, the invisible gravitational scaffold, makes up about 27%. And the dominant component, a staggering 68%, is the mysterious dark energy. This precise accounting acts as a strict judge for any theory attempting to explain dark energy. The patterns in this primordial glow constrain how this force could have behaved over billions of years, telling us whether it has remained a constant presence or evolved as a dynamic field like Quintessence. It is the ultimate anchor for our cosmic models, a foundation upon which we build our search for the universe's hidden architecture, a search that now extends to the vast cosmic web woven between galaxies. This cosmic whisper from the beginning of time reveals a universe built on a scaffolding of dark matter, but the structure we see today tells an even more dramatic story. Look out across the deepest maps of the cosmos, and you will find it is not a uniform soup of stars. It is a vast, intricate web, a cosmic architecture of brilliant galaxies strung along filaments that stretch for hundreds of millions of light years. These great walls of matter surround cavernous, nearly empty voids so immense they defy comprehension. This entire structure is a fossil record, a living chronicle of an epic battle that has been raging for billions of years. On one side is gravity, the great architect patiently pulling matter together. On the other is dark energy, the great repellent relentlessly pushing space itself apart. In the early universe, gravity held the upper hand. Tiny quantum ripples from the Big Bang, imprinted on the cosmic microwave background, were amplified by gravity's relentless pull. Over eons, these slight overdensities attracted more and more matter, growing into the first stars, the first galaxies, and eventually the vast clusters and filaments we observe today. But as the universe expanded and grew more diffuse, the balance of power shifted. Dark energy's influence began to dominate. Think of it like this. In a dense, young universe, gravity's local pull was strong enough to overcome dark energy's global push. But as space expanded, matter thinned out and gravity's local grip weakened. Dark energy, whose strength is tied to the volume of space itself, became the dominant force. This did not just make the universe expand faster, it began to actively suppress the growth of the largest structures. It became much harder for new superclusters of galaxies to form, as the fabric of space between potential partners was stretching too rapidly for gravity to ever pull them together. This tug-of-war leaves a distinct fingerprint on the cosmic web. By meticulously surveying the positions and distances of millions of galaxies, projects like the Dark Energy Survey are essentially creating a three-dimensional map of this structure. They measure how galaxies clump together and how that clumpiness has changed over cosmic time. The subtle ways in which the web has been stretched and thinned provide an independent and powerful measurement of dark energy's strength and nature. Does the data show the growth of structure slowing down exactly as a cosmological constant would predict? Or is there evidence that the repulsive force has been changing, altering the blueprint of the cosmos in a way that only a dynamic field like Quintessence could explain? The architecture of the cosmic web is more than a beautiful spectacle. It is a direct window into the force that holds our ultimate fate in its grasp. The very fabric of space can act as a lens magnifying the distant cosmos. Einstein's theory of general relativity revealed that mass warps spacetime, and this curvature deflects the path of light itself. A massive object like a galaxy cluster becomes a natural telescope, bending and distorting the light from galaxies that lie far behind it. Sometimes this creates spectacular cosmic mirages, multiple images of the same distant quasar or beautiful, stretched arcs of light encircling a foreground cluster. But these distortions are more than just celestial curiosities. They are a precise measurement tool. By carefully analyzing how the light is bent, astronomers can map the total mass of the lensing cluster. This includes not just the stars we can see, but all the invisible dark matter that provides the bulk of the gravitational pull. This technique, known as gravitational lensing, turns gravity itself into our guide. There is a more subtle version of this effect that paints an even broader picture of the cosmos. Instead of creating dramatic arcs, weak gravitational lensing imposes a faint, coherent distortion on the shapes of millions of distant galaxies. It is as if you are looking at a distant landscape through a gently warped windowpane. The images of countless background galaxies are ever so slightly stretched and aligned by the vast, invisible scaffolding of dark matter that lies between them and us. By surveying huge swaths of the sky and measuring these minuscule distortions, we can create a three-dimensional mass map of the universe. This map reveals where matter is clumped and, crucially, how that clumping has changed over billions of years. This is where dark energy enters the story. Remember the cosmic tug of war between gravity and dark energy. Gravity wants to pull matter together to build structure, while dark energy's relentless push works to stretch space and suppress that growth. Weak lensing provides a direct measure of who is winning. By observing how the clumpiness of matter has evolved from the distant past to the present, we can see the imprint of dark energy slowing down the growth of the cosmic web. It is a geometric probe using the bending of light to trace the history of the universe's expansion and the invisible force that drives it. This powerful technique allows us to see the unseen, not with light, but through the subtle warping of spacetime itself. Another echo from the dawn of time is frozen into the cosmos, a vibration that gives us a cosmic ruler. In the universe's first hot, dense moments, it was not a silent place. It was a seething ocean of particles and radiation, a plasma so thick that light was trapped, bouncing endlessly between particles. In this cauldron, gravity would try to pull matter inward, creating an overdense region. But the intense radiation pressure would fight back, creating a powerful outward push. This battle set off colossal sound waves, spherical pressure fronts that raced outward through the primordial soup at more than half the speed of light. Then the universe cooled just enough for atoms to form. The plasma cleared, the universe became transparent, and in that sudden moment, those racing sound waves were instantly frozen in place. Their journey stopped dead, leaving a lasting imprint on the distribution of matter. The result is a subtle but incredibly important pattern. Think of it like a single, massive pebble dropped into the early universe, creating a ripple that expanded and then suddenly solidified. This ripple left a shell of matter, a spherical overdensity with a very specific radius. As the universe evolved and galaxies formed, they were more likely to form along these ancient, fossilized shells. This created a subtle preference for a certain distance between pairs of galaxies in the universe. This is the Baryon acoustic oscillation, a standard ruler etched into the very fabric of the cosmos. We know its true physical size from our understanding of the early universe, a size imprinted by the speed of sound in that primordial plasma. By looking out into deep space, we can measure how big this ruler appears to be at different distances, and thus at different times in cosmic history. If the universe were not expanding, this ruler would always look the same size, but we see it stretched. When we observe this ruler in the relatively nearby universe, it appears stretched by the expansion that has occurred since the light we see left those galaxies. When we look at galaxies billions of light years away, we are seeing the ruler as it appeared billions of years ago. By comparing the apparent size of this cosmic yardstick at different epochs, we can measure with extraordinary precision exactly how much the universe has stretched over billions of years. This gives us a direct, clean measurement of the expansion history, independent of the flicker of distant supernova or the subtle warping of gravitational lensing. It confirms the acceleration and tightly constrains the nature of the force behind it. Is dark energy a simple constant, or is it something that changes? The unwavering size of this frozen sound wave across the ages tells us the answer is written in the silent spaces between the stars. Our most precise measurements of the cosmos are now telling two different stories. This is the Hubble tension, a stubborn crack appearing in the very foundation of our cosmic model. It revolves around a single, crucial number, the Hubble constant, which tells us how fast the universe is expanding today. We have two primary ways to measure this number, one that looks back to the universe's infancy and another that observes its recent life. The first method uses the cosmic microwave background, that ancient whisper of the Big Bang. By analyzing its intricate patterns, we can project forward, calculating what the expansion rate should be right now. This early universe method gives us one answer. The second method looks at the local, modern universe. Astronomers use pulsating stars called Cepheids variables and brilliant supernova as cosmic mile markers. By measuring their distances and how fast they are moving away from us, they get a direct present-day measurement of the expansion rate, and this is where the mystery lies. The value from the early universe is consistently lower than the value measured in our cosmic neighborhood. The universe, according to these local observations, seems to be expanding faster than the ancient light says it should be. This is not a small experimental error. The gap is significant, and it has persisted despite ever more precise observations. What if this tension is not a mistake, but a message? It could be the first direct observational clue that our standard model of cosmology is incomplete. Perhaps dark energy is not the simple, unchanging cosmological constant we have assumed. Maybe it is a dynamic field like Quintessence that has evolved over billions of years, subtly altering the expansion rate in ways we are only now detecting. This discrepancy could be a faint signal of new physics, a ghostly fingerprint of a force more complex than we ever dreamed. Resolving this puzzle is one of the most urgent quests in science, for a crack in the model is often where the light of a deeper truth begins to shine through. This staggering contradiction is known as the Vacuum Catastrophe, and it forces us to peer into the true nature of nothingness. What we call empty space is a lie. The quantum vacuum is not a serene, static void. It is a vibrant, chaotic, and fiercely active medium, a seething ocean of potential. According to quantum field theory, every point in space is occupied by invisible fields, the fundamental entities from which all particles arise. These fields are never truly at rest. They are constantly fluctuating, quivering with a fundamental energy. Think of the surface of a pond on a windy day, but at a scale trillions of times smaller than an atom. These quantum jitters manifest as virtual particles, pairs of particles and antiparticles that spontaneously blink into existence, borrow energy from the vacuum for an impossibly brief moment, and then annihilate each other, returning the energy loan. This endless, frantic dance of creation and destruction is not some theoretical fantasy. We know it is real because it produces measurable effects, like the subtle shift in the energy levels of atoms. This quantum frenzy should fill every cubic centimeter of space with a colossal, explosive energy. When physicists calculate the expected density of this vacuum energy, the result is not just large, it is absurd. It is a number with 120 zeros after it. This titanic force of repulsion should have violently inflated the universe to infinity in a fraction of a second after the Big Bang, making the existence of stars, planets, or life utterly impossible. Yet here we are in a cosmos that is, by comparison, remarkably calm and stable. The actual observed value of dark energy is almost zero, a whisper so faint it is barely there. How can the cacophony of the quantum world result in such a deafening cosmic silence? This is the heart of the catastrophe. Our two most powerful and successful theories of reality are telling us two completely different stories about the fundamental fabric of the cosmos. General relativity, which masterfully describes the force of gravity and the large-scale structure of the universe, tells us that empty space can have a gentle, uniform energy. Quantum mechanics, which governs the bizarre world of the atom, tells us that empty space should be a raging inferno of energy. Both cannot be correct as they currently stand. The vacuum catastrophe is the clearest possible signal that we are missing a crucial piece of the puzzle, a deeper theory that can reconcile the war between the very large and the very small. This conflict pushes us to question the very essence of reality, asking what truly lies beneath the illusion of empty space. This vibrant quantum sea is the true ground state of reality. Forget any notion of a perfect, featureless emptiness. The vacuum of space is not nothing. It is a physical medium humming with latent potential. It is the lowest possible energy level of the quantum fields that fill the cosmos, a foundation upon which everything is built. These fields are not just mathematical abstractions. They are real entities, an invisible lattice that permeates every point in the universe. The electron field, the quark field, the electromagnetic field, they are all there, everywhere, even in what we perceive as absolute nothingness. Their lowest energy state is not zero. It is a state of minimum but persistent activity. This fundamental energy is the source of the quantum fluctuations that define the vacuum. The constant jittering of these fields manifests as virtual particles. A particle and its antiparticle partner can spontaneously emerge from this energy, borrowing from the universe for a time so short we could never directly see them. They exist just long enough to obey the uncertain principles of the quantum world before they collide and vanish, returning their borrowed energy. This endless dance is not just a theoretical idea. We can see its consequences in a lab. Take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum. Classically, nothing should happen. But in our quantum reality, something remarkable occurs. The space between the plates is so narrow that it restricts the kinds of virtual particles that can pop into existence. Outside the plates, a wider variety of fluctuations can occur. This difference in quantum activity outside and inside creates a subtle pressure, pushing the plates together. This is the Casimir effect, a measurable force born from the structured energy of the void. It is direct proof that the vacuum is a something, a system with real properties and a tangible structure. This leads us directly to the heart of the vacuum catastrophe. If this seething quantum foam has so much inherent energy, why does it result in the incredibly gentle, almost negligible push of dark energy? Why is the cosmos not torn asunder? The quantum vacuum is dynamic and wildly energetic on its own scale, yet the dark energy we observe is incredibly smooth, uniform, and faint. Reconciling this vibrant, chaotic microcosm with the serene, expanding macrocosm is the greatest challenge in physics. It is a problem that our current theories cannot solve, a screaming contradiction that demands a new vision of reality, one that unites the laws of the quantum world with the force of gravity. This is the final frontier, the quest for a theory of quantum gravity. To reconcile this screaming contradiction, we must look beyond particles to the fields that create them. The universe, at its most fundamental level, is not built from tiny, solid dots. It is composed of vast, invisible entities that stretch across all of space and time. These are quantum fields, the true bedrock of reality. Think of the cosmos as an immense, silent ocean. This ocean is not made of water, but of countless individual fields, one for every type of fundamental particle. There is an electron field, a quark field, a neutrino field, and even the famous Higgs field. These fields are everywhere, permeating every cubic centimeter of the universe, from the heart of a star to the deepest, emptiest void. What we perceive as a particle is not a separate object, but a localized excitation, a tiny ripple or vibration in its corresponding field. An electron is simply a brief, concentrated hum in the everywhere present electron field. When an electron and its antimatter partner, a positron, collide and annihilate, it is not the destruction of matter. It is merely the calming of a ripple in the field, with its energy being redistributed. This field-centric view, known as quantum field theory, is the revolutionary framework that successfully merges the bizarre rules of quantum mechanics with Einstein's special theory of relativity. It provides the mathematical language for the standard model of particle physics, our most accurate description of the universe's building blocks and their interactions. This theory explains with stunning precision how particles can be created and destroyed, and it masterfully describes 3 of the 4 fundamental forces. The electromagnetic force is carried by ripples in the electromagnetic field, which we call photons. The strong and weak nuclear forces are mediated by their own unique field vibrations, the gluons and the W and Z bosons. Yet, for all its power, this magnificent framework hits a wall when it confronts the 4th force, gravity. Our best theory of gravity, Einstein's general relativity, describes it not as a force in the quantum sense, but as the curvature of spacetime itself by mass and energy. Trying to describe gravity as just another ripple in a hypothetical gravitational field within quantum field theory leads to mathematical nightmares and infinite, nonsensical answers. This failure to incorporate gravity is the single greatest unsolved problem in fundamental physics, a chasm between our understanding of the very large and the very small. It is at this precipice that we must search for a deeper truth, one that can finally unite all of nature's forces into a single, coherent picture. That very idea of an invisible cosmic field was proven real in a tunnel beneath the Swiss-French border. In 2012, the Large Hadron Collider at CERN announced the discovery of the Higgs boson, a particle that sent shockwaves through the world of physics. This was not just the discovery of another particle, it was the confirmation of something far more fundamental, the Higgs field. This field is a cosmic molasses that fills every corner of the universe, an invisible entity that gives mass to the most basic building blocks of matter. Think of empty space not as a true void, but as a vast, quiet room filled with an unseen crowd. When a fundamental particle, like an electron, moves through this space, it interacts with the Higgs field. Some particles, like photons, slip through with ease and remain massless. Others wade through as if moving through a thick crowd of admirers, their progress slowed by the constant interactions. This resistance to motion is what we experience as mass. Without this subtle drag, electrons would have no mass and would zip away at the speed of light. Atoms could never form, and the complex structures of stars, planets, and life would be impossible. The Higgs boson itself is merely a fleeting ripple in this all-pervasive field, a tiny splash of confirmation that the field is truly there. This discovery was a watershed moment, proving that the properties of our tangible world are dictated by invisible, cosmic fields. It sets a powerful precedent for our search for dark energy. If one unseen field can so profoundly shape the universe by giving particles their substance, could another, even more mysterious field be responsible for tearing the cosmos apart? The Higgs field shows us that the vacuum is not empty. It is a stage filled with actors that define the very rules of reality. But this magnificent standard model is not the final word. It is a brilliant yet incomplete chapter in our cosmic story. It masterfully describes 3 of nature's 4 forces and the dizzying zoo of particles, but it leaves profound questions unanswered. Why is gravity so unimaginably weaker than the other forces? A simple magnet can lift a paperclip, effortlessly overcoming the gravitational pull of the entire Earth. This staggering difference in strength, known as the hierarchy problem, points to a deep gap in our understanding. Furthermore, the model offers no particle that could be dark matter, nor does it incorporate gravity itself. To solve these puzzles, physicists look to theories that extend beyond the known, and one of the most elegant ideas is supersymmetry. Supersymmetry proposes a profound and beautiful symmetry at the heart of reality, a kind of cosmic partnership. It suggests that for every known particle of matter, called a fermion, there exists a superpartner particle that is a force carrier, a boson. And for every known force carrier, there is a superpartner that is a matter particle. This would essentially double the number of fundamental particles in the universe. The electron, a fermion, would have a bosonic partner called the selectron. The photon, a boson, would have a fermionic partner called the photino. This elegant pairing is not just for mathematical beauty. It could solve multiple cosmic riddles at once. One of the lightest of these hypothetical superpartners, such as the photino, could be perfectly stable and invisible, making it an ideal candidate for the mysterious dark matter that holds galaxies together. Supersymmetry would also provide a natural solution to the hierarchy problem, stabilizing the mass of the Higgs boson and preventing it from being driven to impossibly high values by quantum corrections. Perhaps most compellingly, it could allow the 3 forces of the standard model to unify into a single, primordial force at extremely high energies, a key step toward a complete theory of everything. The hunt for these superpartners has been a major goal of the Large Hadron Collider. So far, none have been found, which tells us that if they do exist, they must be much heavier than their known counterparts. This lack of discovery is a puzzle in itself, but the search is far from over. Finding even a single superpartner would be a revolution on par with the discovery of the Higgs boson, reshaping our understanding of the quantum world and potentially revealing how the energy of the vacuum itself is woven into the fabric of spacetime. This radical shift from particles to strings redefines the very essence of reality. What if the universe's fundamental building blocks are not tiny, indivisible dots, but unimaginably small, vibrating loops? This is the core proposition of string theory, a breathtakingly ambitious framework that seeks to weave together gravity and quantum mechanics. These strings are thought to be so small that a single atom would be as vast as our entire solar system in comparison. Their magic lies in their vibration. Just as a single violin string can produce different notes depending on how it is plucked, a single fundamental string can manifest as different particles simply by vibrating in a distinct way. One specific resonance might correspond to an electron, another to a quark, and another to the particle that carries the gravitational force, the graviton. In this elegant symphony, all of nature's particles and forces emerge from the harmonious vibrations of these infinitesimal strings, offering the first plausible route to a true theory of everything. Yet this beautiful idea comes with a profound and startling requirement. For the mathematics of string theory to hold together, to avoid absurdities and contradictions, the universe cannot have just the three spatial dimensions of length, width, and height that we experience every day. It needs more. The theory demands a total of 10 or even 11 dimensions for its equations to be coherent. So where are these extra dimensions? The leading idea is that they are compactified, or curled up into shapes so incredibly tiny that they are completely hidden from our perception. Imagine a long, thin garden hose viewed from a great distance. It appears to be a simple one-dimensional line, but if you could shrink down to the size of an ant and crawl onto it, you would discover its two-dimensional surface, a cylindrical landscape that was invisible from afar. Our universe could be like that hose, with 6 or 7 extra spatial dimensions curled into a complex, microscopic shape at every single point in space. This geometric hiding place for the extra dimensions is called the Calabi-Yau manifold, a shape of exquisite mathematical complexity. This is where string theory makes a direct connection to the mystery of dark energy. The specific way these extra dimensions are folded and twisted determines the properties of the vacuum, including the energy density we observe as the cosmological constant. In this view, the incredibly small, non-zero value of dark energy is not a random accident or a calculation error. It is a direct consequence of the particular geometric configuration our universe settled into. String theory suggests a vast cosmic landscape of possible vacuum states, each with a different geometry for the hidden dimensions, and thus a different value for the vacuum energy. Our universe, with its peculiarly faint dark energy, would simply be one possibility among a near-infinite multitude. This idea transforms the vacuum catastrophe from a paradox into a question of cosmic architecture. Why does our universe possess this specific, finely tuned geometry that allows for galaxies and life? The answer might lie in the subtle, silent vibrations of strings in a reality far richer and more layered than we ever perceived. This elegant idea of a cosmic landscape leads to one of the most profound and controversial possibilities in all of science. If string theory allows for a near-infinite number of distinct vacuum states, each with its own unique geometry for the hidden dimensions, then each of these states could manifest as a separate physical universe. This is the multiverse hypothesis. Our entire cosmos, with all its hundreds of billions of galaxies, would be just one single bubble in a frothing, eternal cosmic foam. In this staggering vista, each universe could have a completely different set of physical laws and fundamental constants. The strength of gravity, the mass of an electron, and the density of dark energy could all be random variables set to different values in each of these countless cosmic domains. Suddenly, the mystery of our incredibly small dark energy density finds a potential, if unsettling, explanation. It is an environmental selection effect, a cosmic version of the anthropic principle. In the overwhelming majority of these universes, the cosmological constant is likely to be enormous. In those realms, the repulsive force of dark energy is so violent that space inflates apart in an instant, tearing any potential structure to shreds before it can even begin to form. No stars, no planets, no complexity, and certainly no observers can ever arise. We, by the very fact that we are here to ponder the question, must inevitably find ourselves in one of the exceedingly rare bubbles where the dark energy value is anomalously small. A universe where the push is gentle enough to allow gravity billions of years to sculpt galaxies and forge the elements of life. This explanation does not solve the fine-tuning problem so much as it relocates it. The question shifts from why does our universe have this specific, oddly small number, to why do we find ourselves in this particular hospitable corner of a vast multiverse? For many scientists, this is a deeply unsatisfying answer. It feels like giving up on a fundamental, causal explanation, trading a puzzle in physics for a question in statistics. It is currently untestable, as these other universes would lie forever beyond our observational horizon, disconnected from our own space-time. Yet, the multiverse remains a compelling frontier of thought because it represents a radical shift in our cosmic self-image. It suggests that the deepest laws we are trying to uncover may not be universal, immutable decrees, but merely the local bylaws of our own cosmic neighborhood. The haunting silence of dark energy could be the faint signature of our universe's place within an immeasurably vaster and more strange reality. This principle forces us to confront a deeply unsettling possibility about our own existence. The anthropic principle states, quite simply, that the universe we measure must be compatible with the presence of conscious life that can do the measuring. In its most straightforward form, this is a statement of pure selection bias. We could not possibly find ourselves in a cosmos where the fundamental forces were so out of balance that atoms, stars, or planets were impossible. We are here because this particular universe allows us to be. When applied to the ghostly whisper of dark energy, this logic offers a stark resolution to the vacuum catastrophe. The cosmological constant is not zero, but it is almost zero. If it were just slightly larger by a factor of 10 or even 100, the repulsive force would have overwhelmed gravity in the universe's infancy. Space would have inflated apart with such violence that no galaxy would have ever condensed from the primordial gas. The cosmos would be a cold, dark, and utterly lifeless void. Our existence, therefore, is contingent on a number of breathtaking precision, a value so finely tuned it seems like a miracle. This is where the principle takes a more controversial turn. The strong anthropic principle suggests the universe must have properties that allow or even necessitate the emergence of life. For some, this feels like giving up on a deeper physical explanation. It does not tell us why the dark energy density is this specific tiny number. It only tells us that in a universe where it is not, we would not be around to wonder about it. This shifts the question from a problem of physics to one of probability and observation. Are we the beneficiaries of an inconceivably lucky cosmic lottery ticket, or is there a reason woven into the fabric of reality itself that demands observers? The anthropic argument finds its most powerful, and some would say its most troubling, home within the multiverse concept. If a near-infinite number of universes bubble into existence, each with randomly different physical constants, then it is no longer a miracle that one of them got the numbers right. We simply had to arise in one of the rare, hospitable islands in a vast sea of sterile realities. Our universe is not special, it is just survivable. This idea divides scientists. For its proponents, it is a logical extension of cosmology and string theory's landscape of possibilities. For its critics, it is an untestable retreat from the core mission of science, which is to find causal explanations for the world we see. Yet, whether it is a profound insight or a philosophical cop-out, the anthropic principle forces a humbling perspective. It inextricably links the grand cosmic story to our own fragile presence within it. The silent force shaping the fate of all galaxies may be the very same reason we are here to witness their light. The silent force that allows our existence also writes our final epitaph. If dark energy remains a constant presence or evolves only slowly, the cosmos is destined for a long, cold, and lonely conclusion known as the Big Freeze. This is not a dramatic explosion, but a slow, inexorable fading. The first sign of this end will be a profound cosmic isolation. The accelerated expansion driven by dark energy will eventually push all galaxies beyond our local group faster than the speed of light. This does not violate Einstein's laws, for it is space itself that is stretching. One by one, those distant islands of light will cross a cosmic horizon, their light no longer able to reach us. The universe beyond our immediate galactic neighborhood will simply vanish from the sky, leaving behind an eternal, inky blackness. Within our own galaxy, the party will also wind down. All the gas and dust clouds, the raw material for new stars, will gradually be consumed. The last star will flicker to life, a final ember in a dying cosmic fire. Over trillions upon trillions of years, every star, from the most massive blue giants to the longest-lived red dwarfs, will exhaust its nuclear fuel and burn out. Some will end as white dwarfs, cold spheres of carbon and oxygen that glow with only residual heat. Others will collapse into neutron stars or black holes, silent sentinels in the dark. The universe will grow not only dark but also profoundly cold. As space continues to expand, the wavelength of the leftover radiation from the Big Bang will be stretched into insignificance. The temperature of the entire cosmos will plummet, inching closer and closer to absolute zero, the point where all molecular motion ceases. This is the state of maximum entropy, a final, universal equilibrium where no energy is available to do any work. No stars will shine, no planets will orbit, no chemical reactions will occur. Every process that consumes energy, from the fusion in a star's core to the metabolism in a living cell, will have ground to a permanent halt. Time itself may become meaningless with no events to mark its passage. This bleak, frozen end is the direct and sobering consequence of a cosmos ruled by the repulsive force we call dark energy. The same hidden secret that allowed galaxies to form by delaying its own dominance ultimately ensures their dissolution. It is a future that underscores the profound urgency of our quest, for understanding this force is the only way to know if this chilling fate is truly sealed, or if a more dynamic and mysterious destiny still awaits the cosmos. Yet the Big Freeze is not the only possible finale. A far more violent and immediate end could await the cosmos, a final act of destruction so total it would unravel reality itself. This is the Big Rip, a scenario born from the most unsettling possibility for dark energy. If this mysterious force is not the gentle, constant push of the cosmological constant, but a dynamic form of quintessence that grows stronger over time, then the fate of the universe would be one of catastrophic disassembly. The expansion of space would not merely accelerate, it would intensify without limit, becoming a cosmic hurricane of repulsion. The end would begin on the largest scales. The immense gravitational bonds holding entire clusters of galaxies together would be the first to snap. Galaxies that have danced around each other for billions of years would be suddenly flung apart, their mutual gravity rendered useless against the overwhelming stretch of space. Next, the fabric of individual galaxies would be torn asunder. The Milky Way, Andromeda, and all their stellar companions would be shredded, their stars scattered into the deepening void like dust in a gale. As the phantom force of dark energy continues to amplify, it would turn its attention to smaller and smaller structures. The gravitational embrace that holds our solar system together would fail. The sun would be ripped from its planets, and the planets themselves would be flung from their orbits, becoming lonely voyagers in an ever-expanding emptiness. But the destruction would not stop there. In the final, harrowing moments, the force would become stronger than the very forces that hold matter together. The intense gravity binding a star would be overcome, and the star itself would be violently pulled apart. Then, the electromagnetic forces that bind atoms into molecules and solid objects would surrender. The Earth, a spaceship, a human body, all would be explosively disintegrated into a cloud of disconnected atoms. In the last fraction of a second, the expansion would grow so powerful it would exceed the nuclear strong force, the mightiest bond in nature, which holds the nuclei of atoms together. Protons and neutrons would be blasted into a soup of quarks and gluons. Space-time itself, the very stage of reality, would be ruptured beyond recognition. The universe would not fade into cold silence, but would end in a flash of ultimate disintegration. Current observations of the cosmic expansion slightly favor the more gradual Big Freeze, but the door to the Big Rip remains firmly open. Our ultimate fate hinges entirely on the precise and still unknown equation of state for dark energy, a single number that determines whether this phantom force will one day become strong enough to tear apart the fabric of existence. This relentless expansion may be the very engine of time itself. We experience time as a one-way street, an arrow that flies from the past toward the future. This is not just a feeling, it is a fundamental law of nature called the second law of thermodynamics. It states that entropy, a measure of disorder, always increases in a closed system. Think of a drop of ink in a glass of water. It starts as a concentrated, ordered blob, but it always spreads out, mixing into a uniform, disordered solution. It never spontaneously gathers back into a single drop. The universe is the ultimate closed system, and its entropy is always increasing. This is the arrow of time. But what gives this arrow its direction? The answer may lie in the silent force of dark energy. As the universe expands, it creates more space, and with more space comes more possible ways for matter and energy to be arranged. This ever-growing volume provides an ever-growing arena for disorder to increase. The cosmological expansion, driven by dark energy, essentially winds up the universe's clock, giving time its perceived forward direction. Without this expansion, the arrow of time might not point so clearly. Some physicists take this connection even further. They propose that dark energy is not just a backdrop for our existence, but a prerequisite for it. A universe without this acceleration might collapse back on itself too quickly, or expand so slowly that it never develops the vast, complex structures we see today. The gentle, persistent push of dark energy ensures a long-lived and stable stage, one where gravity has billions of years to sculpt galaxies and stars, where planets can form, and where the slow, intricate dance of chemical evolution can eventually give rise to life and consciousness. In this profound view, our very ability to perceive the flow of time, to remember a past and anticipate a future, is intertwined with a mysterious force that permeates the void. The largest scale force in the cosmos might be written into the most intimate fabric of our experience, connecting the fate of the universe to the fleeting moment of a thought. This ghostly influence cannot be caught in any laboratory trap. Dark energy presents a fundamentally different challenge than its cosmic counterpart, dark matter. While dark matter, for all its elusiveness, still interacts through gravity in ways we can map and hope to one day capture through rare particle collisions, dark energy offers no such handle. It appears to be perfectly smooth, an intrinsic property of space itself that does not clump around galaxies or form halos. There are no dark energy particles to stream through a detector, no specific signal to isolate from the background noise of the universe. It whispers only through its effect on the cosmos as a whole, a subtle but relentless pressure on the fabric of space-time. Our entire understanding of this force is built on inference, on reading the cosmic tea leaves of distant supernova, the frozen sound waves of Baryon acoustic oscillations, and the warped light of gravitational lensing. We do not see the wind, we only observe the bending of the trees. This indirect path is our only way forward. The next generation of astronomical observatories is being built for this singular purpose. Missions like the Nancy Grace Roman Space Telescope and the Euclid satellite are not simple cameras. They are cosmic cartographers of the highest order. They are designed to scan vast swaths of the sky, measuring the positions and shapes of billions of galaxies across cosmic time. By constructing a three-dimensional map of the universe's large-scale structure with phenomenal precision, they will trace the history of the cosmic expansion and the growth of structure with a clarity we have never before possessed. They will look for the slightest variations in how structure formed, seeking the imprint of dark energy's repulsive push as it suppressed the clumping of matter over billions of years. This is a forensic investigation on a universal scale. The quest is not to capture a particle, but to measure a shadow, a persistent absence in the data that points to the presence of a force that is slowly, silently, determining the destiny of everything. But what if our cosmic detective story has been following the wrong suspect entirely? The entire premise of dark energy rests on our faith in Einstein's theory of gravity, general relativity, to be the final word on cosmic scales. Yet a small but resilient group of physicists proposes a radical alternative. Perhaps there is no mysterious energy tearing space apart. Perhaps we simply do not understand how gravity itself works in the vast, near-empty realms between galaxies. This idea is known as modified gravity, and its most famous incarnation is modified Newtonian dynamics, or MUND. The core proposition is deceptively simple. What if Newton's and Einstein's laws of gravity, which work flawlessly in our solar system and in regions of strong gravity, begin to break down where gravity becomes incredibly weak? In the outer fringes of galaxies, where the gravitational pull from the central mass is minuscule, the acceleration of orbiting stars drops to a level billions of times weaker than what we feel on Earth. Mund suggests that at these extremely low accelerations, gravity stops following the familiar inverse square law and becomes stronger. This single change can perfectly explain the rotation curves of galaxies without needing any invisible dark matter halo. Stars in the galactic outskirts orbit faster than expected not because of unseen matter, but because gravity itself is stronger there than our standard theories predict. The success of MUND at the galactic scale is undeniable and was its original motivation. But the real challenge has been to build a complete, relativistic theory that can also explain the largest scale phenomena, like the cosmic microwave background and the accelerating expansion of the universe without dark energy. Some of these extended theories, like tensor vector scalar gravity, attempt to do just that. They introduce new fields that interact with gravity, creating effects that, on the scale of the entire cosmos, can mimic the appearance of an accelerating expansion. In this view, the universe isn't being pushed apart by a phantom energy. It is that the very geometry of space-time on cosmic scales is being subtly altered by a new law of gravitation. The problem is that crafting such a theory is like a high-stakes balancing act. Any modification must precisely explain the anomalous rotations of galaxies and the apparent cosmic acceleration, while simultaneously reducing back to Einstein's flawless predictions within our solar system. So far, no modified gravity theory has managed to successfully pass all these tests at once. The intricate patterns in the cosmic microwave background, for instance, are exquisitely fit by a model that includes both dark matter and dark energy, and replicating that success with a modified gravity model alone has proven extraordinarily difficult. For now, the dark energy paradigm remains the dominant explanation, supported by a converging web of evidence. Yet the persistence of modified gravity serves a vital purpose. It is a necessary and healthy challenge to the mainstream, a constant reminder that our most cherished theories are not sacred. They are maps, and sometimes the most profound discoveries begin when we suspect the map itself might be wrong. We cannot run experiments on the cosmos, so we build digital twins of the universe instead. Inside the world's most powerful supercomputers, cosmologists choreograph the dance of billions of particles, each one representing a vast cloud of dark matter. This is the realm of n-body simulations, virtual laboratories where the entire history of cosmic structure unfolds over millions of processor hours. The simulation begins with a near-uniform soup, its initial conditions seeded by the tiny ripples we see in the cosmic microwave background. Then the clock starts. The force of gravity takes over, pulling particles together over billions of virtual years. Filaments of dark matter snake through the void, knots form where galaxies will bloom, and vast empty bubbles expand. But gravity is not the only actor on this digital stage. The model must include the subtle, relentless push of dark energy, stretching the very grid of the simulated space. Scientists can run the experiment over and over, each time tweaking the nature of this phantom force. What happens if dark energy is a true constant, the cosmological constant? The resulting virtual universe develops a specific pattern of clusters and voids, a particular statistical fingerprint in its cosmic web. Then they change the rules. They program in a dynamic quintessence field, one that grows stronger or weaker over time. In this alternate reality, do galaxy clusters form too early or too late? Is the web of matter too clumpy or not clumpy enough? By comparing these digital universes to the painstakingly detailed maps from real sky surveys, cosmologists can perform a cosmic match test. The simulation that most closely mirrors the real arrangement of galaxies in our night sky holds the key to the true nature of dark energy. These are not just video games, they are our only way to rewind and fast-forward the life story of the cosmos, testing the physics of the void against the grand architecture of everything we see. The most fundamental laws of physics tell us that information can never be truly destroyed. Yet when an object falls into a black hole, it seems to vanish from our universe, taking its information with it. This is the black hole information paradox, a deep conflict between general relativity and quantum mechanics that has puzzled physicists for decades. The resolution may be one of the most mind-bending concepts ever proposed. The holographic principle suggests that all the information describing the contents of a three-dimensional region of space is not stored within that volume at all. Instead, it is encoded on its two-dimensional boundary, like a hologram on a cosmic credit card. A black hole's information is not lost inside its crushing interior, but is smeared across its event horizon, the point of no return. This radical idea, born from the thermodynamics of black holes, forces us to reconsider the nature of reality itself. What if our universe, with its rich three-dimensional tapestry of galaxies and stars, is also a hologram? Some cosmologists are now exploring a breathtaking possibility. The accelerating expansion of the cosmos creates a cosmological horizon, a distant surface beyond which light can never reach us. According to the holographic principle, this horizon has a finite information capacity. The mysterious effect we call dark energy could be the universe's natural response to this fundamental limit. The acceleration may not be driven by some strange energy within space, but could be a consequence of the way information is encoded on the cosmic horizon at the edge of the observable universe. In this view, the force tearing the cosmos apart is not a phantom in the void, but an emergent property of the universe's information storage limits. This is, of course, a highly speculative idea, far from the mainstream, but it demonstrates the sheer depth of the dark energy puzzle. Solving it may require more than just finding a new particle or field. It might demand a complete revolution in our understanding of the most basic concepts we have: space, time, and the very nature of information. Our search for these hidden forces is more than a scientific endeavor. It is a deeply human one that forces us to confront the most profound questions of existence. If the vast majority of the cosmos is made of substances we cannot see, forces we barely comprehend, then what is the true nature of reality? Are the stars and galaxies we observe merely a luminous froth on a dark and alien ocean, a minor side effect of a universe whose true substance is forever beyond our direct perception? This leads to an even more unsettling thought. Does a universe with a dramatic beginning in the Big Bang and a potentially desolate end in a Big Freeze possess any inherent purpose? Or is it simply a vast, impersonal mechanism playing out according to fixed physical laws? The haunting silence of dark energy offers no answer, only the cold equations of expansion. This void where science meets philosophy is where the anthropic principle finds its voice, sparking debates that resonate across disciplines. The apparent fine-tuning of the cosmos, the impossibly precise setting of dark energy that allows for our existence, feels to some like the fingerprint of a creator. To others, it is simply a statistical necessity in a multiverse of infinite possibilities, a cosmic lottery we had to win. There is no easy resolution, for we are using the very minds the universe created to try and discern its ultimate nature. These metaphysical questions are grounded by a very practical, ethical consideration. The pursuit of this fundamental knowledge requires immense investment, from billion-dollar particle colliders buried deep underground to space telescopes that are marvels of engineering. In a world facing pressing crises like poverty, disease, and climate change, is such an investment in pure curiosity justified? It is a valid and vital question. The answer may lie in the unforeseen consequences of our quest. The very technologies developed to probe the vacuum of space, from the World Wide Web born at CERN to medical imaging breakthroughs, often cascade into society, solving problems we never knew we had. More profoundly, this drive to understand our place in the cosmos is a fundamental part of what it means to be human. It pushes the boundaries of our intellect and imagination, inspiring new generations to look up and wonder. The search for dark energy is not an escape from earthly problems, but an expansion of our collective horizon. It reminds us that we are not just inhabitants of a planet, but citizens of a universe, and our journey to understand its hidden secrets is ultimately a journey to understand ourselves. The cosmos does not belong solely to those with a PhD. This grand mystery is a story for all of us, a shared human adventure that you can join from your own home. Across the globe, hundreds of thousands of volunteers have become active participants in the search, contributing to real scientific discovery through projects like Galaxy-Zoo. When you log on, you are presented with images of distant galaxies captured by powerful telescopes. Your human brain, with its remarkable pattern recognition skills, can often classify the shapes of these swirling islands of stars more effectively than any simple algorithm. With a few clicks, you help astronomers sort spiral galaxies from elliptical ones, or identify strange mergers and collisions. This is not a game, it is genuine data analysis, and the collective effort of this citizen science has led to published papers and unexpected discoveries, like the new class of objects known as green P galaxies. This process democratizes discovery, breaking down the walls of the ivory tower and fostering a profound public appreciation for the scientific method itself. It transforms abstract concepts like dark energy and cosmic expansion into a tangible, collaborative quest. This engagement extends far beyond online platforms. Stunning documentaries bring the wonders of the universe into our living rooms, while immersive planetarium shows transport us across the cosmos. Compelling online content from scientists and educators, translates complex research into a narrative everyone can follow. This shared story is vital, for it builds broad public support for the fundamental research that requires significant investment. More importantly, it ignites a spark of wonder in a young person gazing at the stars, potentially inspiring the next generation of astrophysicists, engineers, and dreamers. Our search for the universe's hidden secrets is at its heart a powerful narrative of curiosity and collaboration. It is a testament to our innate drive to explore the unknown, a journey that does not just belong to scientists in lab coats, but to all of humanity. No single field of science holds the key to the universe's deepest secret. Unlocking the mystery of dark energy demands a grand collaboration, a confluence of minds from wildly different disciplines. Particle physicists are essential, for they probe the high-energy regimes of reality, searching for signatures of new fields or exotic symmetries in the shattering collisions of atom smashers. Their quest for particles beyond the standard model, or for evidence of supersymmetry, could reveal the very substances that make up the dark energy field. Meanwhile, mathematicians provide the language for these radical ideas. They develop the complex tools of string theory and the intricate geometries of Calabi-Yau manifolds, crafting the abstract frameworks that might one day describe the hidden dimensions of our cosmos. Without their work, the most profound theories would remain unexpressed, beautiful ideas without a formal structure. This theoretical work then meets the modern power of computation. Computer scientists and data engineers are the unsung heroes, writing the sophisticated algorithms and building the vast digital infrastructure needed to process an incoming flood of cosmic data. They enable the colossal n-body simulations that model the universe's evolution and create the pipelines that sift through the light from billions of galaxies, searching for the subtle signal of accelerating expansion amidst the noise. Even philosophers have a vital seat at this table, analyzing the logical foundations and startling implications of our theories. They grapple with the meaning of a multiverse or the anthropic principle, pushing scientists to clarify their assumptions and consider the broader context of their discoveries. This sprawling, interdisciplinary effort reveals a profound truth about fundamental science. It is not a collection of isolated silos, but a deeply interconnected human endeavor. The most transformative breakthroughs are increasingly born at the boundaries between established fields, in the fertile ground where different ways of thinking collide. The final answer to dark energy will not come from a single brilliant mind working alone, but from a synthesis of diverse perspectives, a chorus of expertise all aimed at deciphering the silent music of the cosmos. Our search for this phantom force has forged tools of almost magical precision. To capture the faint, dying light of a supernova billions of light years away, or to measure the minuscule warping of a galaxy's shape, we cannot rely on ordinary instruments. We have built digital eyes of staggering scale, cameras equipped with billions of pixels that can survey enormous swaths of the sky in a single glance. We launch these observatories beyond the blurring veil of Earth's atmosphere, placing them at a stable gravitational point 1,000,000 miles away, where they can stare into the deep void with unwavering stability. The data they collect is not a simple photograph, it is a fire hose of information, a torrent of petabytes that would overwhelm any conventional computer. This deluge has forced us to invent new ways of seeing, pioneering advanced machine learning algorithms that can sift through the cosmic noise to find the subtle patterns that reveal the influence of dark energy. This technological drive, born from pure curiosity, does not remain locked in an astronomy lab. The same computational techniques developed to map the cosmic web are now used to unravel the intricate structures of proteins or to model the complex dynamics of the global climate. The exquisite sensors designed to catch the faintest photon from a distant galaxy have found new purpose in medical imaging, allowing doctors to peer inside the human body with unprecedented clarity. The quest to understand the universe's expansion has, in a very real sense, expanded our own capabilities. It is a powerful reminder that when we invest in fundamental questions, we are not just buying answers about the cosmos. We are investing in the very engine of innovation, building a future where the tools created to grasp the void ultimately help us improve life right here on Earth. While we grapple with the universe's accelerating end, its beginning holds a puzzle of equal grandeur. Why does the cosmos look the same in every direction? The afterglow of the Big Bang, the cosmic microwave background, shows a nearly perfect uniform temperature across the entire sky. This presents a profound mystery known as the horizon problem. According to the standard Big Bang model, the universe simply did not have enough time for heat to flow between regions that are now on opposite sides of the observable universe. These distant areas were never in contact, isolated beyond each other's cosmic horizons, much like two people standing on opposite sides of a vast ocean with no way to communicate. Yet they managed to reach the exact same temperature as if they had been in perfect thermal equilibrium. How could this be possible? The leading solution is a breathtaking concept called cosmic inflation. This theory proposes that a fraction of a second after the beginning, the universe underwent a spectacular, exponential growth spurt. In an almost unimaginably brief instant, a subatomic speck of space was stretched to a size larger than our entire observable universe today. This violent expansion took a tiny, homogeneous patch, a region that had already achieved a uniform temperature, and blew it up to become everything we can see. The entire cosmos was ironed smooth in that primordial moment, explaining the perfect uniformity we observe billions of years later. While inflation is a powerful and elegant idea, it is not a single proven theory. It is a whole family of models, each with different mechanisms and predictions for what triggered this explosive event, and here lies a tantalizing connection. The engine that drove the universe's explosive beginning, a form of repulsive gravity, might be a close relative of the force driving its accelerated end. Is dark energy the faint, lingering echo of the inflattened field that once dominated the cosmos? We do not know. The physics that governed the universe's first moments remains as hidden from us as the physics of its final fate. Both the horizon problem and the dark energy problem point to a single, humbling truth. Our standard models of the very large and the very small are incomplete. Understanding the universe's birth and its death may be two sides of the same coin, requiring a revolution in physics that we have only just begun to imagine. Our very existence is a cosmic violation, a defiance of a fundamental law. The Big Bang should have been perfectly symmetrical, creating matter and antimatter in equal mirror image amounts. If that had happened, every particle of matter would have met its antimatter twin, and they would have annihilated each other in a flash of pure energy. The universe would be a sea of radiation, empty and dark, with no stars, no planets, and no one to wonder about its origins. Yet here we are, something tipped the scales. A 1 in a billion advantage for matter over antimatter was left over after that primordial annihilation, and that tiny, precious surplus is everything we see, touch, and are. This is the mystery of baryogenesis, the process that generated the slight excess of baryons, the particles that make up atomic nuclei. The physicist Andrei Sakharov outlined the three essential conditions needed for this to happen. The universe's laws had to allow for processes that treated matter and antimatter differently, breaking a fundamental symmetry. There had to be interactions that did not respect the reversal of time, creating a preferred arrow for this asymmetry to build. And finally, the entire system had to be out of thermal equilibrium, meaning it could not be a stable, uniform soup. It needed a jolt, a phase transition, like water suddenly freezing into ice to lock in the imbalance. Our best theory of particles, the Standard Model, does contain some of the ingredients for this cosmic recipe. It has mechanisms that can, in principle, violate the necessary symmetries. But the effect is far, far too weak. The asymmetry the Standard Model can produce is a mere trickle, not nearly enough to account for the vast universe of matter we inhabit. This means we are missing a fundamental piece of physics, a process that was potent and active in the universe's first, searing moments. This profound secret is deeply connected to the other great mysteries of the cosmos. The same violent, high-energy physics that broke the symmetry between matter and antimatter may also have planted the seeds for the cosmic inflation that smoothed the early universe, and perhaps even set the initial conditions for the dark energy that dominates its future. Understanding why there is something rather than nothing is not a separate question from understanding the force that will dictate our ultimate fate. They are different verses of the same cosmic story, a story written in the first fleeting instants of time. Our greatest story of cosmic beginnings is also a story of a profound silence. The Big Bang model beautifully describes the universe's evolution from a hot, dense state, but it offers no answer to the most fundamental question of all. What happened before? The stunning possibility is that this question may have no meaning. If time itself began with the Big Bang, then there simply was no before. In the same way, there is no point north of the North Pole. Our entire vocabulary, built on cause and effect, on a sequence of events, breaks down at this ultimate boundary, yet some theoretical frameworks dare to venture beyond this edge. In cyclic or bouncing universe models, our Big Bang was not the absolute beginning of time, but a violent transition, a cosmic rebirth from a previous state. Imagine the universe not as a single, linear narrative, but as a never-ending cosmic heartbeat. In one phase, the universe expands, driven by a force like dark energy. Eventually, it contracts, collapsing in on itself in a big crunch, only to rebound in a new Big Bang, starting the cycle anew. In these speculative visions, dark energy is not just a force of destruction, but a crucial actor in this eternal drama. Its repulsive push could be the very mechanism that prevents a terminal collapse, providing the gentle nudge needed to initiate the bounce and set the stage for the next cosmic cycle. This transforms dark energy from a phantom of the end times into a midwife of perpetual creation. Probing the nature of time at this boundary is the most profound challenge we face. It forces us to ask not just what the universe is, but what time and existence truly mean, pushing our logic and language to the very precipice of the unknowable. Deep within the faint whisper of the cosmic microwave background, scientists are hunting for a ghostly echo from the universe's first moments. This echo would not be made of light or matter, but of gravity itself. In the instants following the Big Bang, the cosmos may have undergone an unimaginable growth spurt called inflation, where space expanded faster than the speed of light. Such a violent, sudden stretching of the very fabric of reality would have shaken space-time, creating ripples known as primordial gravitational waves. These are not like the waves from merging black holes we detect today. These are the foundational tremors from the birth of the cosmos, a relic from when the entire observable universe was smaller than a single atom. Finding the imprint of these waves is the ultimate goal. As the universe cooled and the first light was set free, these primordial ripples would have left a subtle, twisted signature on its polarization, a specific pattern known as B modes. It is a faint, swirling fingerprint pressed into the oldest light in existence. Detecting this pattern would be a direct window into inflation, confirming a pivotal chapter of our cosmic origin story. The prize is not just confirmation, it is access to energies 1,000,000,000,000 times higher than anything we can create in the Large Hadron Collider. It would let us peer directly into the universe's first fleeting fractions of a second. The search for this signal is a story of extreme precision and humbling challenges. In 2014, a team using a telescope at the South Pole announced a potential detection that sent waves of excitement through the scientific community. But further analysis revealed a cosmic mimic, interstellar dust within our own galaxy, can produce a similar polarization pattern. The signal was not from the dawn of time, but from our celestial backyard. This experience underscored the immense difficulty of the hunt, but it did not end it. Today, a new generation of experiments with even more sensitive detectors continues to scan the cosmic microwave background from the driest deserts and the coldest polar ice, meticulously separating the faint cosmic signal from the dusty foreground of our galaxy. What makes this search so compelling is its profound connection to our other great cosmic mystery. The same kind of repulsive vacuum energy that we see today as dark energy is thought to have powered the incredible explosion of inflation in the past. The field that drove that initial expansion, the inflaton, could be a close relative of the field responsible for dark energy. By finding the signature of primordial gravitational waves, we would not just be confirming our universe's violent birth, we would be measuring the properties of this primordial vacuum energy. This could provide our first real clues about the true nature of the dark energy shaping our future, linking the universe's dramatic beginning to its accelerating end in one unified cosmic story. The silent expansion of space dictates not only the fate of galaxies, but the ultimate destiny of life itself. As dark energy stretches the cosmos toward a cold, thin equilibrium, it sets a final expiration date on the very conditions that allow for complex existence. The era of starlight is finite. All nuclear furnaces, from the most brilliant blue giants to the most miserly red dwarfs, will one day consume their fuel and wink out. The universe will enter a permanent and deepening twilight, a state of maximum entropy where no free energy remains to power any process, from a supernova to a single thought. In this big freeze scenario, any surviving intelligence would face an eternal, resource-depleted cosmos, a clock winding down in an ever-expanding, frigid vault. This bleak horizon forces a profound philosophical question. Is the trajectory of life and consciousness a brief, local phenomenon, destined to be extinguished by the cosmos's underlying architecture? Or could intelligence, given enough time and ingenuity, find a way to persist against the dying of the light? Visionary physicists like Freeman Dyson have pondered such deep time adaptations. Perhaps civilizations vastly more advanced than our own could learn to harness the last available energy sources, like the slow, Hawking radiation evaporating from black holes. Or maybe consciousness itself would transition from fragile biological forms into more durable, simulated states within powerful computers, slowing their internal perception of time to match the eons' long crawl of the cooling cosmos. Yet even these speculative futures have absolute limits set by the relentless work of dark energy. Its gentle, pervasive push defines the ultimate stage, shrinking the available energy and closing the final curtain on all possible activity. The properties of this phantom force, whether constant or dynamic, write the final rules of the game for any future intelligence, no matter how brilliant or resilient. The fate of mind in the universe is inextricably linked to the secret of the void. Our journey through the cosmos has revealed a reality far grander than the world we see. We have followed the trail of dark energy from the runaway expansion of the universe down to the seething quantum vacuum, where empty space is anything but empty. We have weighed the possibilities, from Einstein's simple cosmological constant to the evolving phantom of quintessence, and we have seen how astronomers use everything from the ancient whisper of the cosmic microwave background to the warped light of gravitational lensing to trace this invisible architect. We have dared to explore the radical ideas that might finally offer an answer, from the tiny vibrating strings of string theory to the staggering possibility of a multiverse, each with its own unique laws. This quest forces us to confront our own place in this vastness, asking why a universe capable of giving rise to conscious life is also governed by a force that seems to dictate its lonely end. The mystery of dark energy is more than a scientific puzzle. It is a beacon, a profound challenge that illuminates the limits of our current knowledge and calls us toward a deeper, more unified understanding of reality. It reminds us that the cosmos is stranger, more complex, and more wondrous than we could have ever dreamed. We would love to hear which of these hidden secrets captures your imagination the most. Share your thoughts in the comments and subscribe to join us as we continue exploring the greatest mysteries of the universe. This grand exploration is a living story, and its next chapters are being written right now. You can witness it firsthand by following the work of the monumental observatories leading the charge. The James Webb Space Telescope peers into the deepest reaches of time, studying the earliest galaxies to understand how dark energy began to shape the cosmos. The Vera C. Rubin Observatory will soon begin a 10-year cinematic survey of the sky, watching the cosmic web evolve in near real time. And the Euclid mission is meticulously mapping the dark universe in 3 dimensions, tracing the invisible scaffolding of dark matter and measuring the subtle tug of war that defines our fate. Their public data portals and websites are digital windows into the frontier of human knowledge, open for anyone to explore. Your engagement fuels this entire endeavor. Consider supporting the scientific societies and public outreach organizations that translate complex data into shared understanding. They ensure that this cosmic story belongs to everyone. If this journey into the void has ignited a spark of wonder, you can help keep that flame alive. Share this video with someone who gazes at the stars, subscribe for more voyages to the edge of understanding, and join a community of curious minds. The universe has whispered its first secrets, but the conversation is far from over. Together, we can listen for the next revelation.